welcome everybody to another episode of Video Analytics 101. We're doing this kind of live sessions once per month where we talk to industry leaders and industry experts around topics surrounding video analytics. And the idea here is really to be educational, to provide you more information, to go a little bit into the details of technology and not promote any specific products or push any stuff. This is also not a webinar. There are no slides. This is really a conversation about a specific topic around video analytics. So please also post questions if you have them. We're welcome. We're very happy to answer them. Last month, we talked with iPro and talked about IoT and video analytics, which is super interesting how cameras are becoming IoT sensors. So if you haven't seen this, go over to YouTube, or you are on YouTube right now. After this session, check out this video on IoT together with iPro. This was very interesting. And while you're on YouTube anyway, don't forget to subscribe, because if you're subscribed to the channel, you will get all these nice new videos that we're releasing, which are live interviews, but as well as explainers where we talk about specific things, how things work in video analytics. Today, we have a super interesting topic. Today, we're talking about dark AI silicon and what it is. This is super interesting, and it's a topic that is very important to video analytics, but it hasn't been talked about a lot, and I'm sure many of you haven't heard about it before, and we're gonna clear all of this up today. And to talk about this, I'm super happy to have Nick Nee here with me. He's the Senior Director for Data Center AI and Compute Markets at AMD Xilinx, and he's joining us from the West Coast. So good morning, Nick.
Good morning.
Did you get your coffee?
Yes, right here in my hand.
7 a.m. Super early for you. Cool. So to start us off, maybe let's get into a little bit into the topic. Maybe let's start off with maybe Nick, let's start off with you. Can you explain us a little bit what AMD Xilinx is doing and how does it relate to video analytics? So basically, why are you here?
Sure, that's a great question. And by the way, thank you so much for this opportunity. So AMD, I think many of you may probably know that brand, but most likely I would bet you don't associate AMD with AI. And that's something that's very new. You know, AMD has been very famous in PCs, personal computers, and gaming, right? Now, AI and data centers has been focused. And actually, we've been made a huge amount of progress. This podcast is a great timing because just last weekend, the world's fastest supercomputer was announced. And it's actually announced to be a Frontier from Oak Ridge National Lab. And it's, by far fastest, even compared to a number 2, which is, Japan's supercomputer at the 1.1 exops. And that uses the AMD CPUs and GPUs. So that by itself, I think it proves, whole huge amount of HPC and the machine learning can be done on the AMD GPU and CPUs. And then on the AI training front, I think it was a couple of weeks ago, Microsoft Azure has announced that they're adopting the AMD GPUs for their mass scale training. And we're not talking about the regular AI training, but mass scale with the largest possible models from Microsoft, right? So these are great proof points that we're now making a big step into AI with AMD CPUs and GPUs. And with recent acquisition of Xilinx, which again, one of the largest, I think is the largest actually, the semiconductor acquisition, it brings in the inventor of FPGA. So let me kind of pause here. For those of you who don't know FPGA, it's basically like another hardware that's programmable, right? So unlike any ASICs, purpose built for some kind of functions like cell phone or like, for some 5G chips. This is something you buy, and then you can reprogram this into something exactly for your application. So, it's actually a very popular thing in many of the kind of differentiated use cases, but bringing this into the data center with technology called AI engine, now we're suddenly, even a big player in the AI inference in a much more efficient manner. So all on, AI is such an important market for AMD, and we're really doubling down.
Okay, that's pretty exciting. We haven't, as you were saying, we haven't heard so much of AMD and AI, but it seems like it will become very relevant. So cool to have you here. So the topic today is dark AI silicon, and before we go to dark AI silicon, I want to give a short overview of what dark silicon is, which is maybe a little bit more known. but not so much known to the general public. So in the chip industry, the term dark silicon is very important because it basically says that if you put more and more smaller chips, smaller transistors on a chip, that in theory you would think, okay, it needs to get faster and faster and faster, and the performance compute like increases with Moore's law. But the thing is, if you get down to a certain size, like 8 nanometers, 6 nanometers, heat becomes a problem because all of them emit heat, all the transistors. And it turns out that even if you cram more and more transistors on a chip, turns out you cannot use a lot of them because of heat problems, because you cannot cool this well enough. And this is what we call dark silicon, where you have the performance on a chip, but a large part of it can actually not be used at any point in time. And some people estimate that this is actually 50 to 80% of performance that you have that is not usable. So this is what we call dark silicon in the chip industry, so CPUs and so on. But dark AI silicon is a little bit different. So Nick, maybe can you give us an overview? What is dark AI silicon?
Of course, and you clearly know dark silicon, and you kind of follow the same spirit. So one big difference though is dark AI silicon unintentional by the vendor. So in many cases, dark silicon was something had to make a tough choice. Like you said, they put too much silicon in there, even though the silicon is capable of doing this much work. But because of thermal, most likely it's a thermal reasons, they had to turn off half of it or even more to sustain the packet, whatever the environments you're gonna deploy. Dark AI silicon, on the other hand, is complete opposite. Vendors wanted to unleash the entire power because the AI, as you know, is extremely demanding, right? Compared to anything that was available before, like a traditional computer vision. People say it's easily orders of magnitude more compute you need to do for the same. Of course, the return of investment is huge, right? You get more accuracy, you get more. However, your hardware doesn't need to take on 10x, 100x more sometimes horsepower within probably reasonably same power range and thermal range. So there's a lot of innovation happening, but the problem is AI is not a commodity, right? So this is a workload that continue to change. I'm sure your reapers every day, new innovations happening, new models are being invented. Every time that happens, it puts a different stress or different requirements on how it runs underneath. So because of this, what we see even at the public benchmark data, for example, ML probably heard of, even the best AI GPUs out there achieve 30 to 40% efficiency. What that means is you go pay for, say, the leading AI GPUs, which promise you, say, a couple hundred tops. What you really get in your real models where you execute is most of that. And that's actually the better case. We've seen worse cases where, you take the most modern network, which is really designed for hardware, it runs at like 10%, 20% efficiency. Now, that's quite a big gap, because you were probably planning to unleash most of the horsepower to do your number of stream channels or whatever the applications, but and you are getting like say 1/3 or even quarter that, and that means you're gonna have to add more servers, more capex, just achieve the same original requirements you had, and this is a major problem.
So if I think about video analytics specifically, it means that I might try to run, let's say, one camera on a GPU and see, okay, the camera takes up, let's say, 5% of the GPU power. It's not like I can just extrapolate and say, okay, if I can run one camera at 5%, I can run then 20 cameras in the whole GPU. That's not the case, right? Because at one point it just stops.
That's correct. And unfortunately, the solution there is you have to buy more GPUs to put into your server, or even add more endpoint cameras or even more AI boxes. So, which is definitely not ideal kind of solution, right? The better solution is, of course, to get the higher efficiency. And I do like to explain kind of why that is, right? Because there's actually good reason. It's definitely not intentional, but because we're chasing a moving target, right? Because AI is innovating so fast. Hardware takes time to develop, right? Any kind of CPUs, GPUs, or AI ASICs, at least, right, takes 2 years. And if you include the architectural phase, right, because architecture had to be locked down quite a bit in advance, we're definitely talking about 3 years ago. So anything you see that was launched this year likely was architected 3 years ago or more. So 3 years ago, of course, smart people were doing their best, right, looking at the today's latest models from video analytics, from recommendation, from language models, and then try to predict what is 3 years later. And you know how hard it is, with something like AI. Today we already see transformer, for example, becoming a breakthrough and finding way into everything. How many people could predict it that 3 years ago, for example, right? So I mean, this is a very natural thing, where you do need a programmability into it to future-proof yourself. So what's really happening is so-called feed the beast problem, right? Basically you built a very powerful engine, which is this capable of doing 1,000 horsepower. But if you don't have the work for the engine to do most of the time, the engine is basically idle. And that's exactly what's happening in most of the leading AI GPUs or AI ASICs, because the network workloads changed. And as a result, you just can't pump the data fast enough, and it's low efficiency.
So, but it means that even if I buy a GPU today, I find out there is the dark AI silicon. It's not as efficient as I thought it would be. And in a year, I develop new architecture for a new learning model, then it could get even worse, if I understand correctly, because it's even a newer architecture that the hardware doesn't support.
That's absolutely right. That's absolutely right. So, this is a real problem that, actually every vendor, I would say, is acknowledging, right? One thing that you can see is people are speeding up the chip cycle. So, just look at GPUs, right? I think 2-year cycle is now becoming a norm. Like every 2 years, you're in a new, almost like a whole new GPU architecture. That's really fast. And, if you just go back, I would say 5 years or so, it was more in the 3 years or years, wasn't that, you may get more packs every couple of years, but it's pretty incremental. But we're now talking pretty drastic change, again, driven by this change in the workloads. So that is good, right? That is good that vendors are trying to keep up by working harder, getting more cycles out there. But still, we're talking every 2 years at the fastest. FPGA, on the other hand, you can actually do this quarterly because you don't have to tape out the new chip, you reprogram. Now, FPGA does have some issues as well, right? It's not perfect because there's always a catch, right? You create enough flexibility and adaptability, then you do have to sacrifice a bit of horsepower. So there's always a bit of trade-off, but this program, the adaptability has extremely key in such a fast-changing world.
Okay, so maybe that's a good point. We talked a lot about the problem, so I think we understand it as a problem. So what is a possible solution? So where could we go from here?
Yeah, so this is a $1 million question, right? I don't think anybody has the the one single answer to this, but I think the most obvious to do is to add a hybrid, right, of the very high horsepower or very strong computing power like ASIC has, together with something like FPGA, which has adaptability. Because we're chasing a moving target. I'll be lying to you if I say I know exactly going to be hot 3 years from now. Of course, we try to predict it, but chances are we're going to get 90% wrong. So you have to build in some kind of future proof into your silicon, right? And let's say a year later, a transformer 2 comes up and it completely changes the type of model, right, out there. We still have enough future proof logic that you can change so that you can regain the efficiency. So that's our approach, and I'm sure there are a lot of other approaches as well. But first we're adding this AI engine. It's what we invented and has a lot of programming into products. So this way you get 100 hops on one hand, but also has enough flexibility so you can adapt to the network.
Just opening one bracket here because not everybody might know what a transformer is. Transformers right now that's the new shit, where that might replace existing approaches to deep learning, which is typically CNNs today, that seem to be more accurate and even faster than other things. Right now, it's very popular in language processing, but it's moving to computer vision as well.
Yeah.
we'll see in coming years where this is going. Just an explanation for everybody who doesn't know what it is.
Yeah, I'm glad you said that. Sorry, I kind of dig a little bit deep. Actually, I think might also help say a little bit of evolution of the models, right? Because I think many people remember the breakthrough back in 2012 when University of Toronto researchers and Dr. Hinton has came up with AlexNet, right? And that really grew 10% better results over the decade stalled accuracy of say face recognitions. It was a huge breakthrough, and that's when deep learning became even a people start talking about. But even then, when you look at 2012, the AlexNet was pretty simple model. Without going into too much details, it was really layer after layer after layer. What you mean is you do some kind of math, that you wait for the results, you pass into the next layer, do another math, you pass it to the layer. So pure straightforward, almost like a pipeline, right? So implementing something like that in the hardware was, I would say, pretty straightforward. Only took 1 year. In 2013, Google came up with something called GoogleNet. Of course, today it's already considered very old, right? But that was actually very different. First, they achieved exact same kind of functions as AlexNet, but better accuracy, lower memory footprints. The way they did that was to create much more complex so-called topology, right? So you now not only you're feeding the results from one layer to the next, you're feeding one results to multiple layers, and then you kind of keep on branching, almost like a tree. And then at some point, you're gonna have to converge. And this, in a way, very similar to if you're familiar with Google's map and reduce type of search. It's a huge propagation and then kind of convergence. And just by hearing that, it sounds like much harder to do, right? And it is much harder. So it only took a year for almost all the hardware to go obsolete, and they had to come up with a new architecture. And today, let's say video analytics space, right? A lot of efficient, and these kind of more complex models are becoming popular. And those has another new characteristic, is so-called skip through. So just passing your data to the next layer, next multiple layers, you have to buffer for, let's say, 20 layers, and then use it for the 21st one. Now that is hard because you do have to kind of buffer them in the right place so that it's ready when you need the data. And that kind of stuff really puts a stress in the hardware, and it especially requires some customization in the memory hierarchy caching system to be efficient. So whole kind of get the idea. These are kind of just we're just scratching the surface, but these are kind of changes that really pushes the hardware to keep changing and innovating to with the models.
And let's get back to the solution. You explained it already, but let me just repeat if I understood correctly.
Mm-hmm.
So you were saying basically you think that the solution is a combination between like hardware and the more programmable hardware, the FPGAs, where basically you would I don't know, I guess push a software update, and that would be able to adapt to a new architecture of new types of models. Is that what you were saying?
Exactly. So think of you have a very efficient GPU like cores, right? That can do very similar TOPS or teraflops horsepower, but around it, we'll try to build in very light layer of data flow or basically customizable areas. So for example, today, right? Let's say today's model runs really well on GPUs or even that architecture, and then let's say a year from now, in your company, let's say, your researchers found a very accurate, much better model. However, it just runs, say, half the efficiency on the commodity hardware out there. What we can do is to kind of reprogram that customizable layer. So again, the hardened layer we cannot reprogram. It's very similar to any leading AI GPUs or ASICs. But what's different for us is the customizable layer is a key. You can reprogram them based on the topology I just talked about, right? So that and then we're talking literally like RTL programming. So the hardware engineers or using high-level synthesis can reprogram that so that now your data, instead of getting choked before getting to the engine, can now flow smoothly. So again, you regain the high efficiency by feeding every clock, a data into the engine. So engine has something to do.
Okay. Well, it sounds totally reasonable to me, and it also makes sense that if you buy hardware, you don't basically have to throw it away for after a year when the when the models get updated. There's something to do about it. What do you see the market in general is going to do about it? Because what you just described is obviously the solution of AMD and the approach that you're taking. Do you think that
Mhm.
others will go in the same direction, or are there other approaches where they're going? Where do you think the market is going?
Absolutely, absolutely. And I actually really think everybody's heading a similar direction with a slightly different approach, right?
Mhm.
There's really no, in my opinion, there's really no good, solution for chasing a movie target other than having some kind of future proof. Now, how do you add the future proof? I'm sure every vendor has a different approach, right? So for us, because there's a Xilinx technology that was acquired by AMD, right? So it's very natural to put some of the proven technology like FPGAs or AI engine into it, because that has already proven the things I talked about. Now, I do see, like, for example, some AI ASICs companies, right, or startups would try to use some kind of like a network on chip or programmable. It's still hardened. It kind of builds enough probability between the routers. So that's kind of their approach, right? And then the leading AI GPUs also are introducing more flexibility. With recent announcements, they also expose some of the architectures they're putting to the next generation, and you can clearly see more programmability within the GPUs to do those. So I think this is a common problem everybody's trying to address, which really comes down to how do we regain the efficiency of the hardware as new models come in, because regaining the efficiency means you can get the most number of video streams deployed your applications. If you cannot, your number of video streams will continue to go down, which means you're going to have to buy more servers and more electricity bills.
I really like your summary there, because what it really, why it really matters to us in video analytics, it's really about the amount of cameras you can analyze. I mean, that's what it comes down to. So if you have a project with 100 cameras, it's a difference if you need like 4
Yep.
GPUs or if you need 8 GPUs. So by making it more efficient, we can actually save money, or save our customers money when they're deploying video analytics. So very important topic. Yeah, so super cool. Is there anything else you want to add? Otherwise, I think we have a very good overview already.
Yeah, I mean, this is great. Yeah, it's been my pleasure. So I think I covered everything I wanted to talk about. So thank you so much.
All right. So yeah, thank you for coming. Everybody else, thank you. That's it for today. Thanks for watching. Please don't forget to subscribe below on YouTube so you do not miss the next one. We have the next one scheduled already, so look out for that. And also check out the other videos that were released recently last week about how to calculate accuracy. Nick, thank you again for coming. It's been a pleasure. It's super interesting. People can reach out to you afterwards as well. So he's available on LinkedIn. Check out the Xilinx website, of course, as well. And otherwise, if other people missed this session, send the recording. So thanks everybody for joining. That's it, and see you next time.
Thank you so much.